So we've looked at top six acids and seen that the math for them is very simple. However much top six acid you have, that's how much hydrogen you will get. It's almost the same for bases, except there's a potential wrinkle that isn't going to come up in this first example, and it will come up in the ones after that. So let's take a look. So if we have zero point 0.6 mole per liter sodium hydroxide, this is straightforward because every time one of these hits water, it will break up and we will get one sodium ion, which we don't care about, and one hydroxide ion, which we do. So 0.6 mole per liter NaOH means that our hydroxide concentration will be 0.6 moles per liter. If we have that and we want the hydronium, well, we have a formula that does that for us. H3O is the ion product for water divided by our hydroxide. This formula always looks the same because it's always Kw divided by the concentration you have equals the other concentration. So that makes it fairly easy to remember. If you divide by 0.6, I get 1.67 times 10 to the minus 14, and it is 3 sig digs. So yeah, what I said. 1.67 times 10 to the minus 14 moles per liter for H3O. Not too bad yet. Okay, small difference here. When you put a calcium hydroxide in water, it breaks up and you get a calcium ion. And here's the big difference. You get two hydroxides. You probably saw that coming. So what that means is if you have 0.5 moles per liter of calcium hydroxide and you put that in water, you will get 0.5 moles per liter of calcium, though we don't care when we're doing acid-base stuff, and you will get twice that much hydroxide. So the concentration of OH here is not 0.5. Sorry, that's a minus sign. It's 0.5 times 2, which is 1 mole per liter. A lot of the bases that we use are either group 1 or group 2 hydroxides. So you'll see NaOH, you'll see KOH, you'll see SROH, and you'll also see occasionally beryllium hydroxide, calcium hydroxide, which are 2 to 1. And it is possible to get some threes. I suppose you could do every so often you'll get a 3 to 1 ratio. The trouble is, outside of group 1 and 2, the hydroxides do not dissolve real well in water. So the coefficients you're most likely to see are 1s like this and 2s like this. Just pay attention for this number. If you see it, it means however much of this stuff you put in water, you're going to get twice that many hydroxides. Other than that, none of the calculations change. The OH here is 1 mole per liter. The H3O is the ion product for water divided by, well, 1. That was easy. 1 times 10 to the minus 14 moles per liter for the H3O. Now, let me tweak this. I've been writing 1 a little casually here. The answer here should have 3 significant digits, and so if you have to give this to 3 sig digs, you don't just say 1, you say 1.00. There we are. Okay, a solution prepared by dissolving 200 grams of magnesium hydroxide. That would be MgOH2. Wonder if that 2 is important. In enough water to make 4 liters of solution. We can find the concentration for this by doing number of moles divided by volume, but oh bother, they didn't give us the number of moles. The number of moles is mass divided by molar mass. Mass is 200 grams, they say. Molar mass, let's see, 24.31 plus 2 oxygens would be 32 on the nose, and 2 hydrogens is 2.02. I get 58.33 for the molar mass here. If that's wrong, you may taunt me mercilessly in the comments section. 200 divided by 58.33. 3.4, what do we need? This answer is going to have 3 significant digits, so I'll carry 4 just to cover myself a bit. 3.429. 3.429 moles is probably okay. MgOH2. So our concentration is that number I just said. That's our moles divided by the volume is 4 liters. 3.429 divided by 4, I get 0.8572. moles per liter MgOH2. Now, that is not the end. We need the concentration of hydroxide, and sorry for the crummy flow here. I thought I had a fair bit of space, and it's turning out I don't. The amount of hydroxide in this is going to be twice as great as the concentration of MgOH2 because one of these units contains 2 hydroxides. So 0.8572 times 2 is 1.714. Well, this is a finished answer, so 1.71, I guess. Moles per liter is the concentration of the hydroxide. And the other thing we need is H3O, which is 10 to the minus 14, the ion product for water, divided by 171. 5.85 times 10 to the minus 15. And that's moles per liter. Good. And a few more. Strontium is right after rubidium. It's got a charge of 2, so strontium hydroxide is SrOH2. And 2 moles of strontium hydroxide is diluted to 3 liters. So the concentration of strontium hydroxide would be number of moles divided by the volume is 2 divided by 3. Sorry, my answers are going to have 3 significant digits, so I don't want to just carry 3. I'll carry 1 extra. Okay, 0.6667 moles per liter SrOH2. Now the hydroxide concentration is not this number, it's twice this number because the strontium hydroxide releases 2 hydroxides when you get it wet. So our hydroxide is 0.6667 times 2, which is 1.333. That's moles per liter again. And from that we can get our hydrogen, or our H3O, I should probably say. 1 times 10 to the minus 14 divided by 1.333. 7.50, 3 sigdigs, times 10 to the minus 15. Okay, 150 grams of aluminum hydroxide in enough water to prepare 5 liters of solution. My first thought was, I don't think that this dissolves real well in water unless the water is very hot. But they're saying just wave that off. They want us to do the number crunch, so don't fret the solubility thing. Okay, so we can get a concentration for this by doing number of moles divided by volume. And we've seen this before. They didn't give us a number of moles, so we have to do that also. Number of moles is our 150 grams divided by, now aluminum hydroxide is AlOH3. So the molar mass is going to be 2698 for aluminum, plus 3 oxygens would be 48, and 3 hydrogens is 3.03. I get 7801 for the molar mass. 150 divided by 7801, 1.923 moles of aluminum hydroxide. Okay, now that we have that, we can get around to our concentration here. Concentration is that number of moles we just found. Moles of aluminum hydroxide. Our volume is, they said 5 liters. It's actually in liters for once. So 1.923 divided by 5, 0.3846. 3846 moles per liter aluminum hydroxide. Now the hydroxide concentration is not that number. It's not twice that number either. In this case, it's triple that number. Every aluminum hydroxide releases 3 hydroxides, so 0.3846 times 3 is how much OH we have, 1.1, and this is one of our finished answers, so I need 3 sig digs for this, 1.15. 1.15 moles per liter. Our hydronium concentration is the ion product for water, 1 times 10 to the minus 14, divided by the OH. Should be 8.70, if I'm not mistaken. 8.70 times 10 to the minus 15. Again, that's concentration, so it's moles per liter. And finally, they get the dilution out again. 50 mils of 0.5 mole per liter BaOH2 diluted to 300 milliliters. So, really slick way of doing this, the volume gets 6 times bigger, the concentration will get 6 times smaller. Take this and divide by 6, and that's the new concentration. But, if you aren't comfortable doing it that way, the standard way that always works, the number of moles from this is CV, so it's 0.5 moles per liter times 0.05 liters equals 0.025 moles of barium hydroxide. Now, if we put that in 300 mils of liquid, our new concentration is, well, it's the same number of moles of chemical. We didn't change that. And the new volume is 0.3 of a liter. .025 divided by 0.3, 0.08, endless string of 3's, moles per liter barium hydroxide. Okay, so that takes care of the dilution. We started with this many moles of chemical, we put them in 300 mils of water, and so now we have our barium hydroxide. The hydroxide is twice as great as that. Every time you break one of these up, you get twice as many hydroxides. So our concentration of OH will not be 0.0833. It will be 0.166. Is that right? Yeah. 0.1 endless string of 6's moles per liter. And the H3O, you're probably used to this by now, will be the ion product for water divided by our hydroxide. It's K divided by whichever concentration you have. So 1 times 10 to the minus 14 divided by 0.166. And from that I get 6, pretty much bang on 6. 6 point, yeah, 3 significant digits. 6.00 times 10 to the minus 14 moles per liter. All of these solutions contain strong base, so for all of them we expect to see an extremely low hydronium concentration. If you're a base, it means H3O is pretty much extinct, and that's what we're finding.